So the first point is that I want to discuss today is what impact the addition of creates on the form of the wave function. So in classical mechanics, as you're aware, that the formulation of the problem, that is, if we want to solve a problem using energy conservation, if I shift my potential energy by some reference, overall formulation of it does not have to be the case in quantum mechanics. So if a constant function, it turns out that the wave function picks up a time-dependent factor. That is, now our new wave function can be expressed as times exponential of minus iota v naught t upon h ket. V naught to the potential energy would also alter the form of the wave function. In order to prove this, let us begin with considering the Schrödinger equation whose solution is given by wave function psi. Please note that this solution does not contain an additional v naught as a factor. So psi satisfies the Schrödinger equation without v naught. Now we want to find psi naught, which will say the equation Schrödinger equation modified by the addition of v naught to the potential energy Vx. We want to know that satisfied by the addition of v naught to the Vx. And my claim is that this psi naught would be equals to this psi naught would be simply v naught t upon h ket. So let us see if our claim is true or not. So if it satisfies this equation, then it would be very much clear that due to the addition of v naught, our waveform exponential of minus iota v naught t upon h ket. Please do remember that this psi is the solution of the in which the potential is simply Vx. It does not contain the term. It does not contain the addendum v naught. So let us start. So we claim that now changes to this, and this wave function psi naught would indeed satisfy this differential if our claim is right or wrong. And please do remember this v naught, sorry, this psi x is that solution addendum term v naught. So let us start. So iota h ket del psi naught upon del t would be simply equals to iota h ket. It should not be okay. So del psi by del t. Remember, this psi satisfies the Schrödinger equation without v naught. Psi, since it satisfies the Schrödinger equation without psi naught, so this satisfies this equation. Let's say equation number 1. Satisfies this differential equation. So this psi satisfies this Schrödinger equation. Okay. Now iota h ket del psi naught upon del t is equal to iota h ket del psi v naught t upon h ket, and then there would be minus iota v naught t iota h ket, and then you have this psi. Now this is equivalent to writing iota h ket del psi h ket del psi upon del t plus v naught. See, this t should not get cancels, and iota is iota square. Iota square is -1. This minus would be added, and times psi. Now please do remember iota h ket. Okay, so I'll replace this here. So what I'll get, I will simply get iota h ket minus of h ket square upon ym del square psi upon del x square plus v naught psi times exponential of minus of iota v naught t was simply equals to my psi naught was simply equals to psi times exponential. If I take it inside, so this term will become psi naught like this, and this term will become psi naught. This term and the psi naught And please do remember this is a partial derivative with respect to x. So basically I can take this here as well. H get del psi naught upon del t is equals to minus of h ket square upon pi m plus vx, v as a function of x times psi naught plus v naught psi naught. Clearly see that psi naught satisfy the new differential equation, new Schrödinger equation, which is this, an equation where your potential contains the addendum term v naught. So basically, psi naught satisfies that differential, that Schrödinger. So in quantum mechanics, if we change the potential energy by v naught, the wave function form would also change. However, in term, the expectation values corresponding to the dynamical variable will not change. The expectation values of the dynamical variable will not change. Will not change due to the addition of v naught. Why? Because we know that to some psi naught, which is equals to psi times exponential of minus iota v naught value of a dynamical variable a cap. Previously, when v naught was not added, then my a cap, the function is normalized, psi star a cap psi. But now the new dynamic variable psi naught star a cap psi dx. Now just remember that if exponential iota v naught t upon h get here, and here I will be getting exponential minus iota, and eventually I'll be left with this. So the expectation value of a dynamical variable remains invariant by the addition of so this is worth noting. In the previous class also, we've seen that using time independent Schrödinger is equal to a certain wave function, and from wave function from potential one can find the wave function. Now, can we find the energy given some energy eigenfunction? Yes, indeed we can. So let us take an example to understand the case. So let us consider of mass m moving in one dimension under the influence of a potential Vx, and it is such tends to infinity, Vx tends to 0, given a ground state eigenfunction, psi x is equals to a times, we want to calculate the ground state energy. Here a and lambda are positive constants. Okay, so how to go about it? Problem. Just remember that d by dx of secant hyperbolic x is simply minus secant d by dx of tangent hyperbolic x is simply secant square hyperbolic x square is simply equals to secant hyperbolic square x. And we are already given the state psi x is equal to a secant hyperbolic lambda x, and potential is such that ground state energy from all these given hints. Okay, so let us start. So given that psi x is equals to a, what will happen when kinetic energy operator operates on this wave function psi? So it is equals to minus lambda a secant hyperbolic lambda x will be like h ket square lambda a upon twice m, and then del by del x of this. If I do it, I will simply get a lambda minus secant hyperbolic x and again a tangent hyperbolic lambda x. This is like what about this? So I'll get plus lambda secant hyperbolic lambda x into secant hyperbolic lambda. Derivative of tan hyperbolic x is secant square hyperbolic x. Now from here it is quite clear that minus h ket x square is equals to h ket square lambda square upon twice m times a, and inside we have this secant hyperbolic square lambda x instead of tan square lambda x plus secant hyperbolic q lambda x. This is okay, this lambda goes out. del square psi upon del x square is simply equals to hk square lambda become plus. So I'll get 2 times secant hyperbolic cube lambda x minus secant hyperbolic lambda x common. I will simply get hk square lambda square upon twice m secant hyperbolic, and this a would also come. So this will be like 2 times independent Schrödinger equation. So time independent Schrödinger equation is this. Please remember that this E would represent the ground state energy. This represents the ground state energy. We have calculated this already. So this is equals to hk square lambda square upon twice m times 2 times psi plus v as a function of x times psi is equal to E psi. And we have already been given that as x tends to infinity, that secant hyperbolic x after all is equals to 1 upon cos hyperbolic x. This would tend to 0, but this goes to infinity. So overall, this goes towards 0. So this goes to 0. So over m minus of like, minus 1, this will go towards 0 as x tends to infinity. Vx will go to 0 as e, because this remains constant. E is a constant. So whether even if I take x as large, would be minus hk squared lambda square upon twice. So given ground state eigenfunction, and this one more important you can say way of there may be questions on this also. Now, regarding the solution of the Schrödinger equation. Okay. So in the large class of problems, the Schrödinger no such time dependence, and it is simply the position of it is only simply a function of potential, only depends upon position and not on time, and this remains the subject of our study. Hk del psi upon del t is equals to simply hk psi, and you know that this hk is a time independent operator. Is not time dependent. Now here, please to understand that in order to solve this, what we did, we used something called as the method of separation of variables. And we found out is simply psi as a function of x times a t upon hk, where E is the corresponding energy eigenvalue to this psi of the time independent Schrödinger equation. Now, there comes an important terminology which is called as the stationary solutions also at times. So let us define something called as stationary state or stationary solution. So a state psi as a function of is called as the stationary state if it takes the form iota et upon hk. Now this state is called as the stationary state. All the physical observables of the state turns out to be time independent. Please stop. And when we want to take, let's say norm, let's just as simple as norm of this wave function will not depend upon the time, and hence the name term comes out to be the stationary state. Okay, so this is at times referred to as stationary state, stationary solution, or even separable solutions from the method of separation of variables. Now, just understand that if I want to take the norm of this, and which certainly will not contain any time dependence, because while on hz, and this will carry the term e to the power minus iota et upon hk. So therefore, this is equal. Finding the norm of this wave function, this time dependence cancels out or time dependence drops out. Similarly, find the expectation value corresponding to that dynamical variable, let's say a cap. And as I told you, that most of the, so if I use this up, basically either it can be, I understand that if I want to find the expectation value corresponding to the dynamical variable, then also doubt that because of this term, nothing is going to change, because when I'll be doing psi, it will be simply e to the power minus iota et upon hk. So basically this equals to minus infinite to plus infinite psi star a cap psi and psi. Okay, and in fact, every expectation value that we get every x time. It does not depend upon time or is simply constant in time. And therefore, the name for states. Basically, these states are called as a stationary state. Another reasoning, another important point regarding these stationary states are that these states or separable solutions or stationary solutions, whichever word you feel like using, you can use. These stationary states are the states energy of definite energy. Okay. So how to establish this? See, understand that if I want to calculate the expectation value, evaluating the expectation value, we can change this psi to small psi. So basically, I use psi, let's get psi dx, psi star, sorry. So we'll simply get E minus is simply equals to 1. So basically, we'll get E. Please do understand that h cat when operates on this quite evident. So basically, the expectation value of h cat is simply the total energy E. On psi, we'll get h cat E psi, because h cat again E will come out and h cat psi will again give E. So this is E square. Now, if I want to find the expected infinity, psi star h cat square psi d psi, which is simply equals to E square of h. This will be simply h square expectation value minus expectation E square. And please do remember, what is the physical meaning of this variance? The physical meaning of variance is that the spread around the mean position, or simply how much is the spread of the distribution. And what is the distribution? Here in the context of this, of the values that we get on operating h cat. So basically we know, so therefore every measurement on the stationary state, every h cap measurement energy, because only if there is a definite energy, only then we can say that the no spread in the distribution. So therefore every measurement on the stationary state will yield a definite energy. Okay, understand that the general solution can be written as the linear solution or stationary state. So please do remember that the general solution can be written as the linear combination of these separable solutions or stationary states or stationary. That Schrödinger equation is a linear equation. It's a linear equation. So use a solution that the linear combination of psi1 and psi2 will always be a solution. So if we find some infinitely many collections of solution, let's say psi1, psi2, psi3, psi4, dash, dash, 4, dash, 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 then we can know the wave function at any future times using the stationary state solution. So let's say what I want to convey is that Schrödinger equation. And I get solutions like psi1, psi2, psi3, so on and so forth. Energy eigenvalues are E1, E2, E3, En. The Schrödinger equation has the property that even if they're infinite, even if these are infinite solutions, then all these linear equations, this can be attributed to the linearity of the Schrödinger equation. So the most general form of the general solution will be psi of x comma t exponential time factor, which is minus iota ent upon okay, and if it's Cn, and I will put a summation, because in order to explain the linear combination of all the possible systems, basically this will be the most general form of the solution. This is the most general form of the solution. Okay, so what is the way ahead? Independent Schrödinger equation, then we can always find psi as a function of x at time psi at any future times by writing psi at x comma 0 times exponential term, then this is minus iota ent upon h squared. Please do remember that this is a stationary state. Indeed, this is a stationary state. Okay, linear combination of all the states may not be out of this. So total general solution would be psi as a function of x comma t would be equal to summation n equal to 1 to infinity psi n at x comma ent upon h squared. So here you can clearly see that if would be psi x comma t, please do remember this is not going to be in general a stationary state. Ens will be different and the exponentials may not cancel. Let me consider that a particle start out, let us consider an initial state of the particle, let us say. So let us consider initial state of the particle. So I'm saying that let us say that initially my particle is prepared using two stationary states, let's say psi1 and psi E1, E2 respectively. We want to find the wave function at any future time. So please do remember exponential minus iota En t upon h cat. So if it is 1, so I'll write it as C1 iota E1 t upon h cat plus C2 psi 2 exponential of minus iota E2 t upon h. Maybe if I'm writing a singular thing, like if I'm not writing linear combination, this is clearly a stationary state. Indeed, I will get a 1 here. Indeed, I will get like I will get only psi n mod whole square. I will not get this time dependent term. May or may not cancel each other. So now let us try to find the probability density, or simply psi star psi. It would be simply equals to C1 star iota E1 t upon h cat plus C2 star psi 2 star exponential of iota, this entire thing which is psi. Okay, now if you see, if I take this and this, so this will become so psi whole square, psi1 mod whole square plus C2 mod whole square, psi2 mod whole square, and the remaining terms will still remain. So let's say C2 psi1 star psi2, and this will be like exponential of iota E1 minus E2 2 star C1 psi2 star psi1 exponential of iota E2. You can see that this time dependent term is still there. So probability density does not get rid of when we're expressing the general wave function, or you can say general, so that we cannot get rid of this time dependence. We cannot get rid of this time dependence. It's still there. Okay, and C2 belongs to R. Okay, if we take C1 and C2 both belongs to R, and we take, let's say, science to be real, then as C1 square psi1 square plus C2 square psi2, so simply 2 times C1 C2 psi1 psi2, and then you have exponential iota theta and exponential of minus iota theta. This is simply okay. Sorry, 2 cos theta. Okay, C2 psi1 psi2. This will be C1 C2, and exponential iota theta, and exponential would be theta. Theta would be here E2 or E1 minus E2 upon. You can do it on your own because E1 T upon h squared. So clearly it depends sinusoidally on. Indeed, this is not a stationary state. So I told you initially also that psi and psi2 individually is a stationary state solution, but the linear combination, because these E1 and E2s are separable solution, or simply not a stationary solution. This is one important part one must understand. One must also understand that when I was writing stationary, if it can be expressed in form of, it can be expressed in form of psi x exponential minus, that this E that I'm referring to must be a real quantity, must be a real constant. It cannot be this one which can be written in the form of psi of x comma psi of x times exponent, such that this E belongs to real, or it is a real constant. Okay, I've already the dynamical variables, the expectation value of the dynamical variables, the norm of the function remains time independent. Why this E must belong to R? Let us say that E does not belongs to R minus iota gamma. So here E naught and gamma are real, and I'm considering that expressed in this form. That it would have been expressed in this form. That is, E would have been E naught minus iota gamma. Now, if we want to find what, it would be equals to psi star psi. We will see that this is a stationary state if the probability or the norm of this C. So it will be like psi star. Here I will get exponential iota E star t upon Et upon h squared. And from here it's quite evident that we are getting psi mod whole square exponential of E xt. What is E star minus E? E star minus E would be simply equals to okay. So this probability density or the norm would be simply equals to psi mod gamma t upon h squared. So clearly here this probability term, here this time dependent term does not norm, or while we are evaluating the probability density. So this psi x comma t on h squared does not represent a stationary state if E belongs to complex number, a stationary state. So for a stationary state, this E must be real. Okay. Other way of looking at it is you can say constant and it must be equal to 1. So if I am calculating minus infinity to plus as 1, which is indeed equals to minus infinity to plus infinity from the above analysis, is equals to this. And we know that when we take outside the integration, so we are getting minus infinity to plus infinite psi mod whole squared 2 times gamma t upon h ket is equal to 1. So this will be equal to integral, will give you some value, and when you place the limits minus infinite and plus infinite, this will only you'll get a constant value from this side, that from the left hand side, only if this gamma would be simply E naught belongs to R. So clearly from both ways we can conclude that E cannot be a complex constant, or E has to be a real constant for any normalizable stationary state. Now a few more properties I want to list, which are of the energy eigenstates. So basically I want to discuss all the more property. This energy E, which is inside this exponentially like evident. Now let us discuss some more results. Let us discuss some more results. We know that the time independent Schrödinger equation can be written as minus h ket square plus E minus V times psi is equal to 0. And if I take this negative there, like it will be like psi double dash plus 2, even 2 I'll absorb, so I'll write this. So where epsilon is simply equals to, and this is equals to 2mv upon h ket square. Okay, so a few one-dimensional potential and also pertaining to the bound states. So now we are going to the bound states in one-dimensional potential. Okay, the first thing that one must understand or realize is that there is no degeneracy state in 1D potentials, in one-dimensional potentials. Why so? Okay. What is degeneracy? Degeneracy means two or more than two wave functions are degenerate. Okay. So let us consider the contrary. Let us consider the contrary. Let us psi1x and psi2x are both characterized by the same energy. Let's know what is E. It is equal to me on h ket square. So it implies that when psi1 is Schrödinger equation psi1 star plus epsilon minus nu, psi1 would be equal to 0, and plus epsilon minus nu, psi2 would be equal to 0. If I multiply this by subtract them, what I will get? I will simply get psi2, psi1 double dash, which is equal to taking the derivative of this d by dx of psi2, psi1 dash minus psi2 dash, so psi2, psi1 dash minus psi1 dash minus psi2 dash psi1 must be a constant. Okay, for bound states, psi1 and psi2 both must go towards 0. So it implies that C must be equal to what? 0. Give you 0 minus 0, 0. So C would come out as 0, which implies that psi2, psi1 dash, you can write that ln psi1 would be equals to ln psi2 plus ln k, and which implies that psi1 would be equals to k times psi2. Be different from one another, rather they are equivalent. What we assumed? We assume that psi1 and psi2 are you can say bound states in one-dimensional potentials. It is that the eigenstates or energy eigenstates psi can be chosen real, non-real also, but they can be chosen real also. This is what I want to state. That is, for what you can say of the time-independent Schrödinger equation, that is psi, it can always be taken as real. Or unlike tens and exponentially, some terms exponential minus iota, some et upon necessarily belongs to complex, but psi, which is the solution for the time-independent Schrödinger equation, it can always be chosen real. Okay, it can. Okay, so we want to know that can psi be chosen? Can psi be chosen real? That is, you can always have psi which is real, and the psi. See how. So let us consider possibly a complex wave function that corresponds time independent Schrödinger equation. This is what we've taken, I think, above also. So complex wave function satisfies this equation. Since this complex wave function satisfies this equation, let us conjugation would also satisfy this equation. Okay, conjugation of psi would also satisfy this. Is not equal to psi conjugate. Okay, okay. So basically, if energy, right, they can have the same energy. Now you should not get confused that earlier I told you that two different wave function only. Okay, so these two are different wave functions only, right? So basically, they will define a degenerate solution. Okay, please to understand what I want to convey. Okay, so let us now move to the second property. The second property is that or simply the eigenfunctions or eigenstates can always be chosen real. Can always be chosen real. Right now, I'm not talking about Boxer time-independent Schrödinger equation. Okay, now let us pause our time-independent Schrödinger equation. So let's say that is psi. So psi, let us say the equation. Also understand that if psi satisfies this, then psi star should also satisfy this. And clearly, both of the particular Schrödinger equation for same energy. So clearly, this psi and psi star, both of them form a degenerate solution. Please understand, right now, I'm not talking about one-dimensional. Sorry, I'm not talking about bound states. For bound states and one-dimensional potentials, we cannot have degenerate solution. Right now, I'm not. And psi conjugate forms a degenerate solution. This is clear. And indeed, by their superposition, degenerate solutions. And so therefore, therefore this property comes eigenstates can always be chosen real. See how if I want to create real wave functions, I can create like this. I can a real wave function, or I can do another thing that is psi minus psi star divided. You can say real wave function. So always remember, we can always choose the energy eigenfunctions to be real. In particular, if we are dealing with the bound states, in particular, if we are dealing with states, okay, then one must understand that these two real solutions cannot be different. So they have to be equal, or they have to be equal some constant or up to some constant. Let's say psi r constant times psi r. This is the only width we can have, because understand that for bound state psi im would be some constant times psi r. And what is psi r and psi m? Psi im. These are that the solution for the time independent Schrödinger equation can always be chosen real, or if the equation can always be chosen real. Let us see how. Initially, I just took a complex wave function, let's say equation, time independent. So clearly, psi star also satisfies this equation. Since psi and psi star solution, please do remember, right now I'm not talking about bound states. Now, by the real wave function, and clearly both of them are going to satisfy, being the linear combination. They are time independent Schrödinger equation. The solutions can be real. Plus, if at all they are bound states of one-dimensional potential, it can be said that any solution up to a phase is a state, mean that these two real solutions are equal up to a constant. Okay, so please do remember, admit any. Okay, so another property that I want to discuss is that if Vx is symmetric, an even function, or Vx is an even function, that is V of is an even function, that is V of minus x is simply equals to V of x, can always be chosen either even or odd. This is an important property. Please do remember, eigenstate can chosen either be even or odd. So under the transformation of x to minus x, please do equals to del square upon del of minus x square. Both of them are same. Both of them are same. So if I do the same of the time-independent Schrödinger equation. Psi is the solution for the time-independent Schrödinger. Mu psi is equal to 0, or simply psi as a function of x, psi as a function of x equals to 0. E minus mu times psi as a function of x. Now, if we replace x by minus x, what I will get? I will simply get psi mu times psi minus x is equals to 0. Why have I not changed is given to be equals to v? So clearly 2m v minus of x upon h function of x upon h kt square, which is simply equals to mu. So therefore, this does not get changed. Okay. Somebody may get confused and may ask that minus x be a solution. Will psi minus x be a solution of Schrödinger equation with the same energy, epsilon? Our psi of minus x is simply, let's say, phi of x. Okay, this implies that d by dx of phi minus 1. And if I take the double derivative, I'll get d square phi upon dx square equals to, again would come minus plus 1. Remember, if I'm writing d square phi upon dx square, then this would be equals to d square phi upon minus mu times phi. Now let us move to the third property, an important property in this regard. Or Vx is an even function, then psi x, that is the energy eigenstates, may be chosen odd or even. See, if psi x, and what is an even function? Please remember, a function is said to be even if would be equal to simply v of x. Okay, so if v of x is an even function, then v of minus x should be equal to v of differential equation, which is the Schrödinger equation, minus h kt square upon twice m psi x should be equals to a minus v times. I'm going to write this way so that you don't get confused. Now, instead get minus h kt square upon twice m psi of minus x is equals to e minus v of minus x minus h kt square upon twice m, sorry, del square upon del x square, del square upon del x square. So I'll get psi of minus x. Since v is an even function, so v of minus x remains vx. So from here it is quite evident that psi of minus equation. And also one must understand that this forms a degenerate solution. So it can satisfy the Schrödinger equation for the same energy, capital E. So basically both of them are degenerate. And remember, if we focus on the bound states, one can understand that there's no such degeneracy. So psi of x, which would then imply that psi of x would be equals to c times psi of minus if x is replaced by minus of x. So if x is replaced by minus of x, I'll prove it in general also. So for bound states, since there is no such degeneracy, because we've known that degeneracy, then psi of minus x should be equals to some constant times psi of x. So therefore psi of x is then psi of minus x. Instead of psi of minus x, I can write psi of x here. Psi this c square psi of x. So clearly psi x cannot be 0. It implies c has to be equal to plus minus 1. It implies psi of minus x can either be equals to psi of x if c is equal to 1. So psi of x can either be even or odd. Now, if it is not bound states, in general, it is true. What is true? That if potential Vx is given to us as an even function, then psi x can either just think about this. Clearly, if it Vx is even, then V of minus x should be equals to V of x. Now minus I is equals to E minus Vx psi. This will be like I write x here and then write so minus h cat square upon twice m del square psi minus x so I'll simply write V of x and psi minus x. So clearly I know that psi of x is also solution, psi of minus x is also solution. Now let us choose two solutions. So psi plus would be equal to psi plus psi x plus psi minus x, and psi minus would be simply psi of x minus of psi function. Clearly this is an even function. Why this is an even function? You can understand that psi plus minus x. So if I replace x by minus x, one can clearly see that this is equals to psi minus x plus psi of x. One can say that if Vx is given to be a symmetric potential or even potential, whether we choose an even or odd, whether we consider the bound case and whether we or we not consider, see that we can always choose psi to be either even or odd. Okay, I hope it is clear, and one can clearly both of them satisfy the Schrödinger equation. So it is always possible to choose even as well as odd eigenstates as a symmetric potential. So for symmetric potential, or whenever Vx is an even function or a symmetric function, then functions or corresponding eigenfunctions in general or corresponding wave functions in general will either be even or bound state. It was quite clear because you understand that for bound states in one-dimensional potentials, x or constant times psi of x, and when I evaluated this constant, this turned up to be plus minus x, or psi of minus x is equal to minus of psi x. So in general, for bound state, it is if I'm not considering bound states, then understand that if psi x is solution, then psi minus x is also solution for the linear combination I have made by this. This is an even function, this is an odd function, one can verify. So understand if Vx is supplied to us, which is an even function or a symmetric function, then we can always have or odd. This is a very important property. Now let us move to last very important property, and then we'll finish this property here. What is this property? The property is that E must exceed, that is the total energy, E must exceed the minimum value of Vx every for every normalizable solution to the time. The total energy E must exceed the minimum value of Vx for a normal equation. Okay, just pay attention. Just pay attention to what I say. So time independent Schrödinger equation can be written as this. So I'm writing it here. So what is time independent Schrödinger equation? Time independent Schrödinger equation is simply del psi would be simply dependent upon x is equals to 2m upon h ket square e minus v x from there. Okay. Now, if E does not exceed minimum value, then it implies that E must be less than V minimum. If E is less than V minimum, okay, if E is less than V minimum, then what will happen? This will remain positive. Then I can say that if and if psi is negative, then psi double dash will also remain negative. Just understand always that is this bracket will remain positive. If psi is positive, if psi is negative, then psi double dash would be negative. Okay. Now what does it mean? If I'm going to make a little bit of graph, I've taught you that let's say if psi is positive, then I'm going to make the graph on the above the x-axis. So I'm first considering the case possibilities. Either psi dash is positive or psi dash is negative. If psi dash is positive, so I just assume that either psi dash would be positive or psi dash is negative, or both of them are possible. Let's say psi dash positive and psi dash negative, both can come. Less than V minimum, then this being positive. Now, if psi is positive, then it implies psi double dash is positive. It implies that the graph would be increasing at an increasing rate. So it keeps on increasing. Understand that if psi is positive, psi double dash must be positive. Clearly, you can see here that if E is less than V minimum, if E would be positive, and if psi is positive, then psi double dash would be positive. but we don't know about the first derivative of psi. So let us take first derivative of psi to be positive. Graph would be increasing at an increasing rate. If it increases at an increasing rate, then clearly as x tends to condition for the normalizable wave functions or bound wave functions. Okay, so as x tends to infinity, psi is tending to infinity. Psi dash is less than 0. Let's say psi dash is less than 0. If psi dash is less than 0, then it would be decay point then where it would cut this axis. See, I told you in the curve sketching lecture what increasing, then there would be a point after which this psi would cross this axis and psi would become negative. So this cannot be, and psi dash can be negative. So if psi dash is positive and psi dash is negative, let's say psi dash is negative at first, it is always positive. If I'm making the graph for psi greater than 0, psi double dash has to be positive. So if psi dash is negative, it goes on increasing, then it increases at an increasing rate. So clearly you can see again as x tends to infinity, your normalizable wave function. The same treatment you can apply for psi less than 0. For psi less than 0, has to be also less than 0. Now, if there can be three cases, psi dash can either be negative, psi dash. So if psi dash is negative, then it decreases at a decreasing rate. So decreasing at a decreasing rate is this. Now clearly it tends towards minus infinity. Again, a violation for normalizable wave function. And similarly, you can possible that it increases at a decreasing rate initially, and then again it would decrease at a decreasing rate. I have only the knowledge of psi and psi dash, psi double dash. I do not have the knowledge of psi dash. So let's say if psi dash is greater than 0, psi double dash is already less than 0. So increasing at a decreasing rate and take. So here clearly as x tends to infinity, your psi is tending towards minus infinity. So one can then this particular time independent Schrödinger equation will not yield a normalizable solution in order to have a normalizable solution to the time independent Schrödinger equation. So I have qualitatively discussed with you. These may not come in directly in the examination, so kindly keep a good preparation of this topic. If you have any doubt, please let me know. Till then, take